Hello friends, welcome to our channel Brain Alive. In this video, we will discuss Opamp shunt and series regulator. This is the block diagram of Opamp series regulator. An Opamp regulator generally consists of these three circuits: control circuit, sampling circuit, and comparator. The unregulated input supply is applied to the control circuit, and this sampling circuit samples a portion of the output voltage and feed it to the comparator, where a comparator compares the reference voltage and the feedback voltage and generate an error signal. According to this, error signal is fed to the control circuit. According to this error signal, this controls the output voltage and increases or decreases the output voltage to maintain it constant. Here, this is the circuit of the Opamp series voltage regulator. This is called the series regulator because this controlling element or the transistor is connected in series with the load. Here, this Opamp works as a comparator, means it compares the voltage at two terminals and gives the output. And this R1 and R2 is used as a sampling circuit. This is a potential divider which feedbacks the voltage at the inverting terminal. Now this Zener diode is used to produce a reference voltage which is applied at the non-inverting terminal. Now we will understand the working of this regulator. We can see here a portion of the output voltage is fed back through this sampling circuit or the potential divider to the input of the inverting terminal. Means the voltage that is developed at the R2 is fed to the inverting terminal of the Opamp, and we can see here that it is a closed loop. Due to this closed loop configuration, these two voltages will be almost same. So as these two voltages will be same, and this V1 is equals to Vz because we are applying a reference voltage here, so V1 equals to Vz. And due to this closed loop configuration and negative feedback, this V1 will be equal to V2, as the voltage is V1 equals to V2 and V2 is equals to Vz. So we can find this V2 voltage using potential divider rule. So V2 will be equals to R2 upon R1 plus R2 multiply output voltage. Now we will put Vz in place of V2. Now manipulating this equation, we will get the output voltage of this circuit. So output voltage will be equals to Vz multiply 1 plus R1 upon R2. So we can find the output voltage of this regulator by using this equation. In this closed loop, if we apply a KVL, we will find that the output voltage equals to V minus VB. This V is the voltage generated by this comparator, and this VB is the voltage drop between the base and the emitter. This voltage is fixed, so Y output will be equals to V minus VBE. Now we'll see how this regulator maintains the output voltage constant. Let us suppose this output voltage increases due to some reason. If this voltage increases due to this voltage divider, V2 also increases, means the output voltage, the voltage across this R2 increases. If this V2 increases according to this equation, this is the output equation to find the output of the comparator. This is A is the gain of this Opamp. So if V2 increase, if this V2 increases, obviously this V will decrease. So as this V decreases, according to this equation, if this decreases, if this term decreases, so this will also decrease. So in this way the output will remain constant. The reverse is also true. If, let us suppose, if this decreases, if this voltage decreases, V2 will also decrease. According to this, if this V2 decreases, V will increase. If V increases, means this voltage increases, V output will increase. So in this way the output will remain constant. The main advantage of this Opamp series regulator is that it provides a good efficiency, but on the other hand it does not provide a short circuit protection. If the output terminals are shorted, then all the components means the comparator or the control element will get damaged. So this circuit does not provide a short circuit protection. Now we'll see the Opamp shunt regulator. This is the block diagram of Opamp shunt regulator. In this regulator, the input supply is given through this RS series resistance, and the control element is connected in parallel with the load. That is why it is called the shunt regulator. Now this is the circuit diagram of Opamp shunt regulator. In this diagram, we can see this controlling element or the transistor is connected in parallel with the load, and the reference voltage is also given by this Zener diode at the inverting terminal, and a sample of the output voltage is taken through this potential divider formed by this R1 and R2. In this circuit also we can see a closed loop formed between the output voltage and the non-inverting input terminal. Due to this closed loop configuration, this V1 and V2 tries to be equal. So as they are equal, and this V2 is equals to Vz, because so V1 equals to V2 equals to Vz, as V1 is equals to R2 upon R1 plus R2 multiplied by output voltage, because R1 and R2 are forming a voltage divider and samples a portion of the output voltage and feeds it to the non-inverting terminal. So this we can find this by using voltage divider rule. Now we see that here V1 is also equals to Vz. So we will replace this V1 by Vz. Now manipulating this equation, we can find out the output voltage of this regulator. Now we'll see how this regulator maintains the output voltage constant. Suppose the output voltage decreases. If this voltage decreases, so the voltage at V1 will also decrease. If V1 decreases, as this is at positive terminal, and according to this equation, V equals to A V1 minus V2, as this is the gain of the amplifier, and this V is the output of this amplifier. As if V decreases, V1 also decreases. If this V1 decreases, V output also decreases. If this decreases, if this voltage decreases, a low IB current will flow, means IB also decreases. If this IB current decreases, IC will also decrease, because IC is equals to beta of IB. So if IB decreases, this IC will also decrease, and if this IC decrease, we can see here, this through this RS, IL plus IC flows. If IC decreases, the voltage drop across this resistor will also decrease. So if this voltage drop decreases, automatically the output will increase. Now we can see through this equation, if we apply KVL through this circuit, means V in plus Vs plus V output equals to 0, minus V in, because we are applying KVL through the outer loop. So minus V in plus Vs plus V output equals to 0. So the V output will be equals to V in minus Vs. So according to this equation, if the voltage drop here decreases, the output will increase, and the reverse also is true. If this voltage increases, output voltage increases, the voltage at this terminal V1 increases. If V1 increases, according to this, if this increases, this will also increase, and if V increases, IB will increase. If IB increase, according to this, IC will also increase, and if IC increase, the voltage drop across this resistor also increases. And if this voltage drop increases, automatically, as more amount is subtracted from this input voltage, so output will decrease. So in this way, the output remains constant in this circuit. The main advantage of this circuit is that it provides a automatic or internal short circuit protection. If the output terminals are shorted, all the short circuit current will appear across this resistor RS and all the components of this circuit will be protected. And the main disadvantage of this circuit is that it provides a poor efficiency because there is a large power loss across this resistor. I hope you like the video. If you like the video, please hit the like button and subscribe the channel. Thanks for watching the video.